Hello, today lecture is about thermal conductivity. It is the extension of our previous lecture on Drude model. Or heat conductivity or thermal conductivity is actually the heat transfer, and it occurs using three different methods. First one is conduction, second is convection, and third one is radiation. In conduction mode of heat transfer, what's happened is that two material of different temperature they are in contact, right? One at higher temperature, another is lower temperature. So with this contact, they transfer their heat, but there is no involvement of mass. Like there is no mass transfer. This way of conduction is called conduction. Heat conductivity is called conduction method, and another second one is convection. In convection, there is actually transfer of mass. For example, this happen in liquid or gases. For example, you have a bath, you put on a hot plate and heat it, which has, of course, the water in it, right? When we heat it, hot water goes up and cold water comes in. So this is a convection. The radiation heating is like it occurs through electromagnetic radiation. So we have electronic conductivity, we also have thermal conductivity. Thermal conductivity. And it is defined as with the symbol K. It is negative of heat per unit time per unit area and per unit temperature gradient. Temperature gradient. So this is temperature gradient. Of course, area, time, and this is heat. This is how actually we define. Now this heat per unit time per unit area is actually, we define it as heat flux. Right. So in this way, we can write this expression as where this is heat flux divided by, or further simplification, we can write or further simplifying it, we can write heat flux equal to thermal conductivity and temperature gradient. This expression one, let's call it expression A, is called Fourier law of heat conduction. Fourier law of heat conduction. Now let's move further and develop thermal conductivity in more detail. In our case, that we are considering that heat is transferring through electron collision. It is occurring because of the electron collision. This is the main component that has led to heat transfer of heat for the from hot end to cold end. Now, to begin with, let's consider example. Sample bar, right? This end is hot and this end is cold. Somewhere between, let's consider a position. Now, what is happening is the basically there is electron are colliding with another electron and transferring its energy. That's how heat is getting propagated, right? Now we is thermal velocity of electrons. In that case, the transfer of or the distance between the electron that is colliding with this imaginary surface will be from hot side will be x minus v top, right? Similarly, from the cold side, it will be h plus velocity and the time between two collision. So there is an imaginary interface, and the heat that is being transferred from hot end to close end by last collision of electron will be x minus thermal velocity multiplied with the time between two collisions. Similarly, from cold end to hot end will be x plus v tau. Right now, the energy that is being transferred is a function of temperature, right? Of course, and that this temperature is actually function of distance, as because it is from going from hot end to cold end. So as the x is changing, the temperature is also changing. As the temperature is changing, energy is also changing. So overall, E is a function of both T, which is a function of x. Right now, to move further and let's develop the question further. Right, let's consider that there are total of anti-electrons in the system. That the system has an anti-electron, and so in that case, there are 50% probability, 51 probability of electron going from left to right, and also 50% probability that it will go right to left. Right. In that case, the heat flux is defined as J equal to total number of particles divided by 2, because the probability is half, velocity, and energy, which is again function of temperature. Then X, right? Now let's write the expression for from hot end to cold end, and also cold end to hot end. Hot end to cold end. Define as J hot end to cold end. It will be NT by 2 V T T and X minus V from, right? Similarly, for cold end to hot end, it will be cold into hot end will be Nt by 2 velocity energy X plus T2, right? Okay, this is expression 1, this is expression 2, right? So net flow will be J hot side to cold side minus J cold side to hot side. If you put this expression, we will get J net equal to Nt by 2 V E E x minus theta minus T by 2 V energy T x minus theta. Now from the approximation of linearity, T x minus theta, we can write it as T Tx minus theta dE by d. Similarly, we can put this into both this expression. So what we will get? G net will be Nt by 2 V, it will be E T x minus V so dE by dx minus E dx minus V so dE by dx. Now this will cancel out. It will become J net. It will become Nt V so dE by dx minus, right? Or it can be further written as minus Nt V square. So dE by dt and dt by dx. And from the previous lecture, we know specific heat of electron at constant volume is Nt E by dt. If you put this into this expression, you will get J net equal to minus V square tau PVE dt by dx. So this expression B, if we compare with our previous expression A, they are very similar. Where the value of thermal conductivity, if we compare from A and B, get A equal to V square from PE, right? But this is the case for 1D. Sorry, this is the case for 1D. But for 3D, 1 by 3 V square. This is the expression for thermal conductivity from Drude model. Now let's summarize the result from this expression and the previous that we actually estimated. The electronic conductivity, which was sigma, it was NT E square so upon M, and thermal conductivity that we just estimated is 1 by 3, and also from the previous equation we know kinetic energy was 1 by 2 P by 2 kVt, and also CV was 3 by 2 kV. Right. These were the value that we estimated from the Drude model, the equation that we came to the Drude model. Now, as we know, you might have also observed that a good conductor of actually electricity is also a good conductor of heat. So for example, metal, they are very good conductor of electricity, but also very good conductor of heat. So this observation was also made by another scientist, and they came up with a experimental law. There were two scientists, were Weidemann and French, and they observed that the ratio of thermal conductivity and sigma T, yes, sigma is electric conductivity, is actually constant, and which is around 2.4 G 10 to the power minus 8 J omega by F square. They observe it. So since we also have all the value of K sigma T, and let's put it and see if it's how true or not. So if we put K, which is the expression is 1 by 3 by sigma and T. So to simplify it, will become 1 by 3 and this square. So, and we will put the value of PV, which is 3 by 2, and PV is square from without which will become, and this square is 1, and we know the kinetic energy, and V square is PKBT. It will be also the velocity. So it will be 3 kb, and of course there was T here. So kb multiplied by A by sigma T from Drude model come out to be E by 2 AB by electrons E electron charge. So these are constant, we know Boltzmann constant, these are also constant. If we put this value and we estimate, it will come out to be around 1.1 10 to the power minus 8. So the value predicted by root model is matching with the experimentally observed behavior. So this is a success of root model, that it is actually predicting the fitting good with the experimental value. But not to carry it away with this thing, because this coming good is actually is a by chance. Why I say by chance? This is coming because in the case that we have this time, or we found that was like this. And what is happening is that the value of specific heat at constant volume derived from the fluid model is actually overestimated. It was actually overestimated by a factor of 100. Right? People have actually experimentally measured this value, like a at very low temperature, so that all the uh, contribution comes from only from the electron, and they found their value to be 100 times lower than the value predicted by Drude model, and the value of mean square value of thermal velocity was underestimated by a factor of 100. So overall, what is the one thing is overestimated, and second term is underestimated. So overall, they compensate each other. So it is by chance that these come out to be true in most of the gases. But if we go into the deep, they are faulty, right? And another important thing about root model is that, as we have also mentioned at the beginning, the assumption that it suppose there is a metal, let's say silver, has positive ions in it all over, right? And then there is a free electron moving around here and there. It assumes that there is no interaction between electron and the positive ion core, and also there is no repulsion between electron to electron. So it's like very strange, right? If there has positive charge, there is a negative charge. There has to bound to be any interaction. So these were the shortcoming of the Drude model that I discussed. There will be improvement on this in the coming lectures, where we will take into consideration of this interaction, and also diverge into briefly into quantum mechanics, just for the brief introduction why there was need and what actually it changes. This will be discussed in the coming. Thanks for your time.